We did Monday of week 4. And the problem I posed was this. Imagine that you have 2 metal plates, and they each have some area, A, and they're separated by some distance, B. And I said, imagine that you have a potential difference between them, and you maintain that potential difference. Well, in order for that to happen, you have to let charge flow. And so it must be connected to both sort of a reservoir / cache for charge. And we know that often as a battery. So it maintains the potential difference, and then things flow until they don't flow anymore. And so when you're in equilibrium, the plates are charged. And they have equal and opposite charge. Okay. So I asked myself, what does potential have to do with charge anyway? The question is, find the ratio of that charge to the potential difference. And I start by thinking about a metal plate. And so if I zoom in, if I take this portion of the problem and I zoom in down here, I have a metal plate with, say, a bunch of charges on it, and it's connected to the system. And so I'm going to do a quick Gauss's law here. I'll say pick a little can. I might as well choose another area, small a. And inside the conductor, I know that the electric field equals 0. And there's no flux through the sides of the can, so the only electric flux actually goes through the end of the can. And so I'll do a quick Gauss's law. E dot dA is sigma over epsilon naught, and I find that the field inside a conductor, just one cap, is equal to, whoops, not sigma, getting ahead of myself, Q enclosed. And Q enclosed would be sigma times that little area, so I'm looking at just the charge in this part of the plate, divided by epsilon naught, and then unfortunately those a's go away, and I'm back to what I was heading for, which is that the field inside a capacitor is sigma over epsilon naught. So the question was, what's the ratio of potential to charge? So I don't really have potential yet, but I remember that the potential difference is the integral of E dot dL. Now, in a lot of these problems, we're just going to be looking at a potential difference. So if we say it's 4 volts, we're not going to worry too much that it's plus 4 volts or minus 4 volts. And so this becomes particularly simple in this problem. So the potential difference is just the integrated electric field, but that's just a constant. So it's sigma over epsilon naught, and my potential difference is maintained between the 2 plates. So the path over which that potential difference is calculated is just D. Okay. So that's pretty straightforward. And so I can go even farther, and I can rewrite this as Q D over A epsilon naught. I've expanded this charge density into a Q and an area because the question that was asked is what is the ratio of that Q to the delta V? And I find that Q over delta V, Q D A epsilon naught. The Q's cancel, and I'm just left with A epsilon naught all over D. And that's the answer, and this ratio has a very special name. This is called the capacitance of a parallel plate capacitor. The ratio Q over delta V for anything is defined as the capacitance C for any system. Okay, I'll stop there.